Can you see the screen right now? Okay. So in this session, we are going to a new topic, which is actually called metal semiconductor contact. Okay. Can give the heading as metal semiconductor contact. Semiconductor contact. This is the topic that we are going to see today. So നമ്മൾ already പഠിച്ചിട്ടുള്ളത്, we have already learned about semiconductor junction or the contact between two semiconductors, right? We have actually formed a junction between p-type and n-type, right? Both are semiconductors, p-type semiconductor and n-type semiconductor, and we have tried to bring them together so that we got a junction called p-n junction. In that case, both the materials were semiconductors, right? p-type semiconductor and n-type semiconductor. So we tried to we tried to create a junction between two semiconductors. But in this case, we are trying to create a junction, or we are trying to create a contact between a metal and a semiconductor. That particular semiconductor can be either n-type or p-type. So that's what this is actually called a metal semiconductor contact. A junction that is formed between a metal and a semiconductor. PN junction diode എന്ന് പറയുന്നത് that was actually a contact between two semiconductors. But here we are actually trying to bring together a metal and a semiconductor. And if we are doing, or if we are creating such a junction between metal and semiconductor, it can behave either as a diode or it may behave like an ohmic contact. Diode at behave in what is that? Diode means it will conduct only in one direction. That is, diode will conduct only when it is forward biased, right? So when a metal and semiconductor are brought together, or when we are trying to form a junction between a metal and a semiconductor, this device or this material can act either as a rectifying diode or it can act as an ohmic contact. Ohmic contact means ohmic contact there will be current in both directions, whereas in rectifying contact there will be current flow only in one direction. Rectification means the current passes only when the diode is forward biased or there is unidirectional flow of current. So this metal semiconductor contact can behave either as a rectifying contact or as an ohmic contact. Ohmic contact means current passes in both directions. So when does this metal semiconductor contact behave in these two conditions? ഈ രണ്ട് രീതിയിൽ എങ്ങനെയാണ് വർക്ക് ചെയ്യുന്നതാണ് നമുക്ക് അറിയേണ്ടത്, അല്ലെങ്കിൽ what is the criteria behind that? So when we form a metal semiconductor contact, I'm saying that sometimes it will behave as a diode, sometimes it will behave as an ohmic contact. So this sometimes, which at which point does it behave like a diode or a rectifying contact? That is a question. So in order to understand that, we need to be familiar with some other terms, which I will discuss right now. For that, one term is very essential. It's called the work function. Based on this work function, is the circuit behaves like a diode or rectifying contact. This is the parameter which judges whether the metal semiconductor contact behaves like a diode or a ohmic contact. So this work function is, I will show the work function in energy band diagram clearly. Now you just be familiar with the terms that are being used. The work function in the case of a metal is determined, or it is denoted as phi m. Okay, phi m is actually the term which denotes the work function of a metal, whereas the work function of a semiconductor is defined or denoted as phi s. Okay, phi SC, semiconductor. Phi SC is the term that is being used for denoting the work function of a semiconductor, and phi m is the term that is used for denoting the work function of a metal. And for getting a clear idea about this, I will just show that the next. Consider an n-type semiconductor. Just consider an n-type semiconductor. How will I draw the energy band diagram of an n-type semiconductor? I have EC over here. Then I have EV over here. If I am telling that this is an n-type semiconductor, where will be the position of Fermi level? Fermi level position will be closer to which energy level? EC or EV, if it is an n-type semiconductor. N-type semiconductor ആണെങ്കിൽ Fermi level will be closer to പെട്ടെന്ന് പറ. If I am considering an n-type semiconductor, Fermi level position EF will be closer to EC. That is, the position of Fermi level will be somewhere around here. Okay. So this is the case of an n-type semiconductor. And in order to explain the work function, you need to be aware of another energy level called the vacuum energy level. This is the vacuum energy level. Okay. Cannot hear vacuum level. Vacuum level. And this difference is called Q phi m. Since this is energy level, I am representing it as Q phi m. This energy level, this energy difference is actually called the work function of the semiconductor. That is the energy level difference between the vacuum level and the Fermi level is called the work function. Vacuum level means in this vacuum level, the electron will be completely free. That is, the electron will be out of the material. If we are considering an n-type semiconductor, vacuum level is considered as an energy level where the electrons are completely free from the material. A vacuum level is considered as an energy level where the electrons which are completely free from the material will occupy. So the energy difference between the vacuum level and the Fermi level of the material is actually called the work function. This is actually called the work function, that is Q phi m, or it is denoted as phi m. When it comes to energy, we are representing it as Q phi m. If you are representing V0 as contact potential, when it comes to energy band diagram, it will become QV0 since we are representing electron volt. Okay, similarly, phi m is a representation for work function, and when it comes to energy level, it becomes Q phi m. Since it's not Q phi m. Since we are considering semiconductor, it will be Q phi SC. So M, this is SC. Since we are considering semiconductor, right? N-type semiconductor, so it will be Q phi SC. Yes, Q phi SC. In general, you can say that work functions are the energy level difference between the Fermi level and the vacuum level. Is that clear? And if you are asked for the the work function of a metal, you will draw it like this. You'll be having the EFM over here. That is the EFM. That is the metal Fermi level of the metal. Okay. FM denotes the metal, and here SC denotes the semiconductor. So, and again you are having the vacuum level, and this difference will be called, that is the energy difference between the Fermi level and the vacuum level. Fermi level of the metal and the vacuum level is called Q phi m. That is the work function of the metal. In general, you can say the energy difference between the Fermi level and the vacuum level is called the work function. When it comes into semiconductor, it is denoted as Q phi SC, and when it comes into metal, it is denoted as Q phi m. Is that clear? This is what we called as work function. Clear? What is work function? Energy difference between Fermi level and the vacuum level. That is called the work function. That is how much energy is required for an electron to be free. Clear on work function? Is that clear? Okay. So this I have already mentioned. Based on this, work function is actually uh, the parameter. Work function is actually the parameter on which the classification of metal semiconductor contact is depending. So how is that classified? That we will see here. Type of contact. Okay. And here you have relative relative work function. And if I am comparing the work functions, if phi m, okay, if phi m, that is the work function of the metal is greater than phi s. രണ്ട് conditions വരാം. I have already told that the work function is the parameter on which the classification depends. Metal semiconductor contact ohmic ആണോ അതോ rectifying ആണോ എന്ന് അറിയണമെങ്കിൽ we need to understand the difference between the work functions. So രണ്ട് രീതിയിൽ work functions differ ചെയ്യാം. ഒന്നുകിൽ phi m can be greater than phi s. In other words, in other condition, it can be phi m can be less than phi s c. These are the two conditions, right? Work functions ഈ രണ്ട് രീതിയിലേ ആവുള്ളൂ. Either it can be greater than phi s or it can be less than phi s. And if we are considering a metal semiconductor conductor, നമ്മൾ consider ചെയ്യുന്നത്, so the semiconductor can be either n type or p type. So metal n type semiconductor contact ആണെങ്കിൽ, metal n type semiconductor ആണെങ്കിൽ, രണ്ടാമത്തെ കേസിൽ മെറ്റൽ പി ടൈപ്പ് സെമി കണ്ടക്ടർ ആണ്. ഈ രണ്ട് കണ്ടീഷൻസ് വരാൻ പറ്റുക. ടൈപ്പ് ഓഫ് കോണ്ടാക്ട് ഏതൊക്കെ രീതിയിലാവും? മെറ്റലും എൻ ടൈപ്പ് സെമി കണ്ടക്ടറുമായിട്ട് കോണ്ടാക്ട് വരാം, ഓർ എൽസ് മെറ്റൽ ആൻഡ് പി ടൈപ്പ് സെമി കണ്ടക്ടർ കോണ്ടാക്ട് ക്യാൻ ബി പോസിബിൾ. So if it is phi m greater than phi se, in case of metal n type semiconductor contact, it will be called, or it will become a rectifying contact. So what is the condition? If in the case of a metal n type semiconductor, that is if we are bringing together a metal and n type, നമ്മൾ മെറ്റലും n type semiconductorും യോജിപ്പിക്കുകയാണെങ്കിൽ, at that time, if the phi m value is greater than phi se, then we will get a rectifying contact. If phi m is less than phi se, in that case we will be getting a ohmic contact. Okay. And reverse is the case in case of metal p type semiconductor. Here phi m greater than phi se ആണ്, p type semiconductor ആണ് നമ്മൾ യൂസ് ചെയ്യുന്നതെങ്കിൽ we will be getting ohmic contact. And here you will be getting rectifying contact. എങ്ങനെയാണ് ഈ ക്ലാസിഫിക്കേഷൻ വരുന്നത്? Two parameters are there. It depends upon which is the type of semiconductor that we are using, and also it depends upon the work function, relative work function difference. How the work functions of the two materials, that is the metal and semiconductor, depends. Metal n type semiconductor ആണ് നമ്മൾ ഫോം ചെയ്യുന്നതെങ്കിൽ, if phi m is greater than phi s, that is the work function of metal, that is this value phi m is greater than phi s, ഈ വാല്യൂവിനെക്കാളും കൂടുതലാണെങ്കിൽ you will be getting a rectifying contact. If it is less than phi s, you will be getting an ohmic contact. When you have taking the case of metal p type semiconductor, if phi m is greater than phi s, you will be getting ohmic contact, and on the other case you will be getting a rectifying contact. These are the classifications. രണ്ട് type of metal semiconductor contacts ഉണ്ട്. Can be either ohmic contact or can be rectifying contact, and this is how you get the different types. And this is based on the work function. I have mentioned what is work function, difference between the Fermi level position and the vacuum level position. And in case of semiconductor, it is denoted as phi se, q phi se, and in case of metal, it is denoted as q phi m. Clear on a basic classification? Okay. നമ്മൾ എനർജി ബാൻഡ് ഡയഗ്രം വരയ്ക്കുമ്പോൾ നിങ്ങൾക്ക് കുറച്ചുകൂടെ ഒരു ക്ലിയർ ഐഡിയ കിട്ടും. ഡോണ്ട് വറി അബൌട്ട് ദിസ്. നിങ്ങൾ കംപ്ലീറ്റ് ചെയ്ത് കഴിഞ്ഞല്ലോ അല്ലേ? I'm rubbing this. Completed, right? Energy band diagram ആണ് ഈ കേസിൽ വളരെ ഇമ്പോർട്ടന്റ് ആയിട്ടുള്ളത്. So initially I am going to discuss about rectifying contact. അതിൽ metal n type rectifying contact is what we are going to see right now. Metal n type rectifying contact. This is also called Schottky contact. SCHOTTKY, Schottky contact. Rectifying contact is also called Schottky contact. We are going to see the energy band diagram of this one, metal n-type semiconductor Schottky contact. So you should draw. I will completely draw once, and after that you just need to copy that. And you can tell me which are the positions. Okay. First, we need the metal n type, right? നമ്മൾ ഇവിടെ p-n junction അല്ല p type ഉം n type ഉം വരയ്ക്കാൻ we are having metal and n type. So on left side you will be drawing the metal energy band diagram, and on right side you will be having the n type semiconductor contact. N type semiconductor energy band diagram. Okay. ഞാൻ വരച്ചു കഴിഞ്ഞിട്ട് നിങ്ങൾ വരച്ചാൽ മതി. Now you just see how I am drawing this. Metal case, you need to represent only one line which represents the Fermi level position. നമ്മൾ നേരത്തെ work function കേസിൽ പറഞ്ഞ പോലെ തന്നെ you just need one line which represents the Fermi level position. I'm drawing this from completely there. Okay. E F M. This is the representation of metal. Metal കേസിൽ ഈ ഒറ്റ line മാത്രമേ ഉള്ളൂ which represents the Fermi level position of the metal. There is no EC, EV and all. Since it is metal, there is no such band. So all the electrons are completely free, right? So we just need a Fermi level that is EFM in case of metal. ഞാൻ ഇനീഷ്യലി വരയ്ക്കുന്നത് നമ്മൾ എനർജി ബാൻഡ് ഡയഗ്രം ഓഫ് പി എൻ ജംഗ്ഷൻ വരയ്ക്കുന്ന സമയത്ത് ഇനീഷ്യലി നമ്മൾ വരച്ചത് ഐസൊലേറ്റഡ് എൻ ടൈപ്പ് ആൻഡ് പി ടൈപ്പ് ആയിരുന്നു. സോ ഹിയർ വി ആർ initially drawing isolated metal and n type semiconductor. So this is metal energy band diagram, and at top, at top we'll be having a common vacuum level. We'll be having a common vacuum level at top that I am going to represent with green. ഇത് നിങ്ങൾ ശ്രദ്ധിക്കണം, കാരണം ഇത് ചോദിക്കാറുണ്ട്, പല ക്വസ്റ്റ്യൻ പേപ്പറിലും ചോദിച്ചിട്ടുണ്ട്. This is what I am calling it as a vacuum level. This I am drawing as common for both metal and semiconductor. So ഞാൻ പറഞ്ഞു this difference is actually called the work function. A work function is actually the energy difference between the Fermi level and the vacuum level. You can touch this position. Okay. And this is denoted as Q phi M. This is actually the energy band diagram of metal. Metal part. And next comes semiconductor. Semiconductor we are using n-type semiconductor. Okay, we are using n-type semiconductor. So we know how to draw the n-type semiconductor. I am drawing it like this. I am drawing EC over here. And I am drawing EV somewhere around downward somewhere around here. EV. Okay. And since I have mentioned n-type semiconductor contact, n-type on the right side of metal n-type semiconductor contact we will be having the Fermi level which is closer to the EC. We will be having EFSC. SC represents semiconductor. And vacuum, here also the phi SC is actually this one. The energy difference between the Fermi level and the vacuum level, which is represented as Q phi SC. Okay, so this is the first figure where you have drawn the isolated isolated metal and N-type semiconductor. There is nothing much. Now we haven't brought them together. We are now going to form the junction semiconductor. On the next level, what we are going to do is we will be drawing the semiconductor metal contact. Now you can analyze. In case of metal N-type rectifying contact, what is the condition for work function? What is the condition for work function? Work function condition in case of rectifying contact, metal N-type rectifying contact, what is the condition for work function? What should be the condition for work function? നമ്മൾ ഓൾറെഡി എഴുതി ബോക്സിൽ എഴുതി കഴിഞ്ഞു. അത് മൈക്ക് ടേൺ ഓൺ ചെയ്ത് പറഞ്ഞോ നിങ്ങൾ? എനിവൺ?
5m greater than 5sc.
5m greater than 5sc. ഈ ഫിഗറിൽ അനുസരിച്ച് 5m greater than 5sc ആണോ? ഈ ഫിഗർ നിങ്ങൾ അനലൈസ് ചെയ്യുമ്പോൾ this is your 5m, this is your 5sc. Is the condition satisfied? Is the condition satisfied? Satisfied ആണോ? നിങ്ങൾക്ക് കണ്ടാൽ മനസ്സിലാവില്ലേ? 5m greater than 5sc satisfied ആണോ? Yes or no? This is your 5m and this is 5sc. Yes, that condition is satisfied. So now you know how to draw this. നിങ്ങളിപ്പം ഈ ഫിഗർ നിങ്ങൾ ആലോചിക്കാൻ എന്തുകൊണ്ട് ഇവിടെ വരച്ചില്ല? ഇവിടെ വരച്ചാൽ എന്താ സംഭവിക്കുക? Your 5sc will be like this. This much will be there. If we start from here, if your EFS lies over here, ഇങ്ങനെയാണ് നിങ്ങൾ ഇപ്പം വരയ്ക്കുന്നതെങ്കിൽ EFS ഇവിടെയാണ് വരുന്നതെങ്കിൽ what happens? Your 5sc will be like this. So 5sc will be greater than 5m. നമ്മുടെ കണ്ടീഷൻ എന്തായിരുന്നു? റെക്ടിഫൈങ് കോണ്ടാക്ട് നമുക്ക് ഫോം ചെയ്യണമെങ്കിൽ our condition has to be 5m greater than 5sc. That is satisfied in this figure. So അല്ലേ, 5m greater than 5sc എന്ന് പറയുന്ന കണ്ടീഷൻ സാറ്റിസ്ഫൈ ചെയ്യുമ്പോൾ you will be getting a rectifying contact. എപ്പോൾ? when it is a metal and N-type semiconductor which are brought together. So the first part is over. We are satisfying the condition 5m greater than 5sc. So when we bring together these two materials, we will be getting obviously a rectifying contact. Is that clear? എങ്ങനെയാണ് ഇങ്ങനെ വരച്ചെന്നുള്ളത് ക്ലിയർ ആണോ? Is that clear? Okay. Now we are going to bring together these two materials. So നമ്മൾ ഇത് രണ്ടും ഒരുമിച്ച് കൊണ്ടിരുന്ന സമയത്ത് you can clearly understand that at equilibrium what will be the condition? നമ്മൾ p-n junction diode വരച്ച സമയത്ത് I have already mentioned. At equilibrium what is the condition? How will we draw the energy band diagram of an equilibrium contact? ഒരു equilibrium contact ന്റെ കേസിൽ how will you draw the energy band diagram? Tell me. Equilibrium കേസിൽ how will you draw the energy band diagram? What is the condition? We can analyze the p-n junction energy band diagram. p-n junction diode ന്റെ കേസിൽ energy band diagram when we mentioned about the equilibrium energy band diagram, what was the condition? Just tell me that. Just check that and tell me that. What is the condition? എങ്ങനെയാണ് നമ്മൾ equilibrium energy band diagram വരയ്ക്കുക? What is the condition for that? When we bring to the two junctions, how will you draw the equilibrium energy band diagram? പെട്ടെന്ന് പറഞ്ഞേ. p-n junction diode ന്റെ energy band diagram നോക്ക്. നമ്മൾ 4 figures വരച്ചല്ലേ? Forward bias, reverse bias, equilibrium. അതിൽ equilibriumത്തിൽ what was the condition for drawing the energy band diagram? നിഖിൽ, ഞാൻ പേര് വിളിക്കുന്നവർ പെട്ടെന്ന് പറഞ്ഞോണം, സമയം അധികം കളയാനില്ല. നിഖിൽ. എനർജി ബാൻഡ് ഡയഗ്രം നമ്മൾ p-n junction diode വരച്ച സമയത്ത് equilibrium energy band diagram നമ്മൾ എങ്ങനെയാണ് വരച്ചത്? ആദ്യം നമ്മൾ ഐസൊലേറ്റഡ് ഫിഗർ വരച്ചു. അത് കഴിഞ്ഞ് equilibrium energy band diagram വരയ്ക്കാൻ നമ്മൾ എന്താ ചെയ്തത്? എന്തായിരുന്നു കോമൺ ആയിട്ട് വന്നത്? സിംഗിൾ സ്ട്രേറ്റ് ലൈൻ ആയിട്ട് ഏതാ വന്നത്? EF അല്ലേ? എന്ന് വെച്ചാൽ whenever you say that the junction has become an equilibrium, is in an equilibrium condition, what you will be doing in energy band diagram is that you will bring together these two Fermi levels. The Fermi levels will align. Fermi levels of metal and semiconductor will align in a single straight line upon when we say that the junction is at equilibrium. Okay, whenever we say that the junction is at equilibrium, you need not worry about any other thing. You just need to draw the Fermi level of metal and semiconductor in a single straight line. Clear or not? That is, EFM will be the same line as that of EFSC. Is that clear? Clear or not? Okay. So how will I do that? So the second case is equilibrium. നമ്മൾ semiconductor, I mean PN ജംഗ്ഷനിൽ വരച്ച അതേ കണ്ടീഷൻസ് തന്നെ. First isolated, then equilibrium, then forward bias, then reverse bias. So here EFM എന്ന് പറയുന്നത് you will be drawing it in a single straight line. ഇതിൽ മാറ്റമൊന്നുമില്ല. EFM എന്ന് പറയുന്നത് കോൺസ്റ്റന്റ് ആയിട്ട് ഈ ഒരു ലൈൻ തന്നെ മെയിൻറ്റെയിൻ ചെയ്യുക. So I will draw EFM over here. This is your EFM. And since this is equilibrium, EFM and EFSC will be lying on the straight line. EFM and EFSC will be lying on the straight line. And since there is a depletion layer that I am drawing initially, since there is a semiconductor, we are having a depletion layer. So equilibrium case, and we are representing it as W naught. So EFSC and EFM will lie on the straight line. EFS. Okay. Now EFS അനുസരിച്ച് ബാക്കി എല്ലാ ലൈൻസും മാറും അല്ലേ? EFS ഇവിടെ വരികയാണെങ്കിൽ അതിന് തൊട്ട് മുകളിലേക്ക് എന്ത് വരിക? EC വരിക. ഈ ഫിഗർ അങ്ങനെ താഴേക്ക് വരികയാണ് അല്ലേ? If this EFS is coming down towards the EFM, every line will go equivalent, I mean same as that of അല്ലേ? EFSC മൂവ് ചെയ്യുന്ന അതേപോലെ തന്നെ EFSC will come here, EC will come just above that, EV also will be moving down. Clear? അങ്ങനെയല്ലേ അലൈൻ ചെയ്യുന്നത്? See, ഈ equilibrium condition നടക്കുന്നത് എങ്ങനെയാണെന്ന് ചോദിച്ചാൽ we will be having electrons over here. These electrons will be moving from this region towards the metal region. So when electrons are moving, what happens? The energy band diagram will come downwards, or the energy level will come downwards, and finally it will align with the EFM. ഇപ്പൊ ഇവിടെയാണ് ഇവിടുന്ന് എനർജി, ഐ മീൻ ഇലക്ട്രോൺസ് ഇങ്ങോട്ട് മൂവ് ചെയ്യാനാണ് എളുപ്പം അല്ലേ? Correct. If you are considering the energy level, the electrons over here can move easily to the metal side, and they will move. When the electrons are moving from this side to this side, this energy level will come down, and finally it will align with the EFM. That's how it happens. So this is EFS, and just above that you will be having EC. അതിലൊന്നും മാറ്റമില്ല, സെയിം അതുപോലെ തന്നെ you will be having EC, and EV ഇവിടെ ആയിരുന്നു initially, it will also move down. EV. Clear? And now you need to represent this EC and this EC level. ഈ EC ലെവലും ഈ EC കൂടെ നിങ്ങൾ ജോയിൻ ചെയ്യുക. Okay, and here also EV and this you will be joining. Okay. And this will be called, നമ്മൾ നേരത്തെ PN ജംഗ്ഷനിൽ പറഞ്ഞ പോലെ തന്നെ, this will be QV0. No difference in that. Depletion layer W0, QV0 is actually the energy difference between EC and the original EC level, equilibrium EC level and the original EC level. Okay. Can draw this. When you complete this, just tell me. ഇങ്ങോട്ട് നമുക്ക് രണ്ട് ഫിഗേഴ്സ് കൂടെ വരയ്ക്കാനുണ്ട് ഇതേ വലുപ്പത്തിൽ. സോ കൺസിഡർ ദാറ്റ് വെൻ യു ആർ ഡ്രോയിങ്. യു നീഡ് ടു ഡ്രോ ദിസ് ഓൺ എ സിംഗിൾ സ്ട്രെച്ച്. ഈ ഒരു ഒരേ ലൈൻ തന്നെ നമുക്ക് വരയ്ക്കാനുള്ളതാണ്. യു വിൽ ബി ഹാവിംഗ് ടു മോർ ഫിഗേഴ്സ്. ഒരു ഫിഗർ ഇവിടെ ഉണ്ടാവും, ഒരു ഫിഗർ ഇവിടെ ഉണ്ടാവും. ദാറ്റ് മച്ച് സ്പേസ് ഷുഡ് ബി ദയർ. Okay, I will just complete this. That will be better. After that, you can draw this. No issues. Okay, so this is the equilibrium case. Now, just tell me the common logic that we often used. When we are forward biasing this, forward biasing means since we are using a metal N-type semiconductor, we are using a metal N-type semiconductor. So, in order to forward bias this material, you need to connect a negative potential to this. Right? N-type ഏത് ബയസിംഗ് ആണോ വരുന്നത് അല്ലെങ്കിൽ ഏത് ടെർമിനലാണോ വരുന്നത് അതനുസരിച്ചായിരിക്കും ബയസിംഗ് മാറുക. So, if we need to forward bias this metal N-type semiconductor, you need to connect a negative terminal to the N-type. If you are doing so, what will be the case of this QV0? എന്നുവെച്ചാൽ forward bias ചെയ്യുന്ന സമയത്ത് how was the barrier changing? When we discussed the case of PN junction diodes, ഞാൻ പറഞ്ഞിട്ടുണ്ടായിരുന്നു already. Whenever we are doing a forward bias, the depletion region width will decrease and this potential will also decrease. Whenever we are doing a reverse bias, the depletion region width will increase and this difference also will increase. So now since I am applying a forward bias, this value or this difference will decrease. Decrease means this has to go move upwards or downwards. ഈ value decrease ചെയ്യണമെങ്കിൽ this has to go, this level has to go upwards or downwards. അത്രയും പറഞ്ഞാൽ മതി, ബാക്കി ഞാൻ വരയ്ക്കാം. Tell me, when I am applying forward bias, I have mentioned that this depletion width decreases. Along with that, this barrier height also will decrease. So in that case, the energy band diagram on the semiconductor part has to move upwards or downwards. ഈ EC എന്ന് പറയുന്ന മുകളിലേക്കാണോ താഴേക്കാണോ മൂവ് ചെയ്യുന്നത് അത് പറഞ്ഞാൽ പറയൂ. നമ്മളിത് പി എൻ ജംഗ്ഷൻ വരച്ചതല്ലേ ഓൾറെഡി. നിങ്ങൾ റെസ്പോണ്ട് ചെയ്യാതെ നമുക്ക് ഓൺലൈൻ ക്ലാസ് ഒരിക്കലും മുമ്പോട്ട് കൊണ്ടുപോകാൻ പറ്റില്ല കേട്ടോ. whether it is correct or not, that is not an issue. You should respond. അല്ലെങ്കിൽ ഈ പറയുന്നതൊക്കെ വേസ്റ്റ് ആവും. എനിക്കിതൊരു പി പി ടി ഇട്ട് കാണിക്കാൻ പറ്റാഞ്ഞിട്ടല്ല. ഐ എം യൂസിങ് ദിസ് ടാബ്ലറ്റ് ആൻഡ് ഓൾ ഫോർ യുവർ റെസ്പോൺസ് ഓൺലി. അല്ലെങ്കിൽ ഞാനൊരു പി പി ടിയിൽ ഈ 4 ഫിഗർ ഉള്ള ഒരു ഫിഗർ കാണിച്ച് എനിക്ക് പഠിപ്പിക്കാൻ അറിയാഞ്ഞിട്ടില്ല. തെറ്റിക്കോട്ടെ, യു ക്യാൻ റെസ്പോണ്ട് റൈറ്റ്. I want this QV0 to decrease. ഈ QV0 value decrease ചെയ്യാന്ന് വെച്ചാൽ this energy level, energy band diagram should move upwards or downwards on the semiconductor side. That is my question. Nikhil. Anas.
Upward.
അതെന്താ നീ ഇപ്പൊ പറയാത്തെ? ഞാൻ വിളിക്കണോ? അനസ് ഉണ്ടോ? അനസ്. ഇപ്പം റെസ്പോണ്ട് ചെയ്യാത്ത ഒരാൾക്ക് പോലും ഞാൻ അറ്റൻഡൻസ് തരില്ല. ഐ എം ടെല്ലിംഗ് ദാറ്റ് ഫ്രാങ്ക്ലി. I will give attendance only to those who are responding in the class. Last attendance number ഇടുന്നവർക്ക് ഞാൻ I will not be giving any attendance. I will check the entire chat. If anyone is not responding in between, I will not give their attendance from today onwards. My question is, QV0 has to decrease when it is forward biased. Similarly, the W0, that is the depletion region width, also will be decreasing when it is forward biased. So how will this energy band diagram change? Whether it will be moving upwards or downwards, that's the question. I want everyone to write their answer in the chat box. No answers. So today nobody is present, right? ക്ലാസ്സിൽ ആരും പ്രസന്റ് അല്ല.
സാർ ചാറ്റിൽ ഇട്ടിട്ടുണ്ട്.
Okay. So this will be moving upwards. How will we draw that? ഞാൻ ആദ്യമേ പറഞ്ഞു കഴിഞ്ഞു EFM എന്ന് പറയുന്ന ലൈൻ ദാറ്റ് വിൽ ബി ഓൺ എ സിംഗിൾ സ്ട്രേറ്റ് ലൈൻ ദാറ്റ് വിൽ നോട്ട് ചേഞ്ച്. നിങ്ങൾ EFM പറ്റി ബോധർ ചെയ്യേണ്ട. EFM എപ്പോഴും നിങ്ങൾ ഇതേ രീതിയിൽ തന്നെ വരച്ചാൽ മതി. So I am drawing the third case which is forward biased. How will I draw that? EFM you will just draw similar to that of previous one. In depletion region width എങ്ങനെ മാറും? It will decrease since we are forward biasing. Depletion region width will decrease when compared to the equilibrium case. Equilibrium case consider ചെയ്യുമ്പോൾ ഇതിന്റെ width കുറയും. So that has got decreased, and now this barrier height also will decrease, which means this EC and all these three lines EC, EFS and EV will move upwards. So I will be drawing EC over here, EFS I will draw here, and EV also move bit upwards. EV I will draw here. So then I will join this height. This height will not change. ഏതാ ഈ EFM ഉം ഈ ലൈനും തമ്മിലുള്ള ഡിഫറൻസ് this is not going to change. This will be remaining as constant. So this height change. ഈ സൈഡിൽ നിന്നുള്ള ഹൈറ്റ് മാത്രമേ ചേഞ്ച് ചെയ്യുള്ളൂ. ഈ സൈഡിലെ ബാരിയർ വിൽ റിമെയിൻ ദ സെയിം. ഏത് സൈഡിലെ ബാരിയർ? ഈ മെറ്റലിന് ഇവിടെ ഉള്ള ഇലക്ട്രോണിന് സെമി കണ്ടക്ടറിലേക്ക് മൂവ് ചെയ്യണമെങ്കിൽ ഇറ്റ് നീഡ് ടു ക്രോസ് ദിസ് മച്ച് എനർജി അല്ലേ? ഈ ഹൈറ്റ് ക്രോസ് ചെയ്താൽ മാത്രമേ ഇവിടെ ഉള്ള ഇലക്ട്രോണിന് ഇങ്ങോട്ട് പാസ് ചെയ്യാൻ പറ്റൂ. An electron from this side will move to semiconductor side only after crossing this much barrier. E energy barrier cross ചെയ്തേ പെടുകോ. Okay, that will not be changing in any biasing. All the biasing cases it will be remaining the same. So now, as I mentioned, this QV0 has got reduced, and this will be എങ്ങനെയായിരിക്കും ചേഞ്ച് ചെയ്യുക? If I am applying VF as a forward biased, if I am applying VF as a forward biased voltage, how will this change? QV0 കുറഞ്ഞ ഒരു വാല്യൂ എങ്ങനെ മാറുക? How will you represent that in equation? നമ്മൾ ഓൾറെഡി ഇത് സെമി കണ്ടക്ടറിന്റെ കേസ് പറഞ്ഞു. How will you represent? Q into എങ്ങനെ ചേഞ്ച് ചെയ്യും? Q into പറഞ്ഞു V0 minus VF. Q into V0 minus VF will be the energy difference when we are considering forward biased case. Next hour ഞാൻ തന്നെയാണ്. Now you can leave for a break. I will give attendance to those who have responded here. Thank you.